Good afternoon. Last time we started talking about chemical kinetics of halogenation of methane. In today's lecture we'll continue developing that theme and we'll slowly get into some more sophisticated cases. But before we do that, we will review some concepts from last time, mostly the concept of the transition state, which we defined as the highest point on this energy curve, which plots the energy versus reaction progress as we go from starting materials to products. And we mentioned that this energy barrier that needs to be overcome is called the activation energy, EA, and it also that this specific point, the highest point in the energy profile, is called the transition state, which is also often denoted by the double dagger symbol. Now the structure of transition state is unique because it's the most unstable structure. It cannot be isolated and in many cases it cannot be experimentally observed either. It is basically something very different from an intermediate, which is an unstable yet isolable in principle product. So the structure of a transition state, in our case, we have bonds between hydrogen and chlorine. Hydrogen and carbon have broken, the bond between hydrogen and chlorine have formed. So this will be our transition state, which would then collapse into methyl radical and HCl. Okay? But now, this is an energy profile of a simple reaction, but the question is what happens in a more complex reaction, a reaction which has multiple steps. And most of the reaction we will study in this course will have multiple steps. So, in fact, the reaction we talked about already, the halogenation of methane, the propagation has two steps. The first one forms methyl radical and HCl, and the corresponding delta H value is plus 1 kilocalorie per mole, while the energy of activation is plus 4 kilocalories per mole. The second step is the reaction of this methyl radical with another molecule of chlorine. And this reaction gives us the second product of the reaction, methyl chloride, plus Cl radical, which re-enters the chain. And delta H in this case is very favorable, minus 25 kilocalories per mole, while the activation energy is also lower, it's just plus 1 kilocalorie per mole. And now we should try to plot this on an energy diagram and see how do these relationships pan out here. And so the first, we basically follow these reactions, these energetical relationships as the reaction progresses. So we start with starting materials, and then we have this 4 kilocalorie per mole barrier for the first activation. And then we end up with our intermediates, which are a little bit higher than our starting material, and this corresponds to this delta H1, while this corresponds to EA1. And remember, this is the first step, and this is the second step. Okay. Now, another activation energy, this time smaller one, gets us over this hill, and this will be EA2, to finally go into the very deep well, which are our reaction products, and this is our minus 25 kilocalories. So this is delta H2. Okay, and this is the overall profile of our reaction. Now here we have our products, here we have our starting materials. This structure, the minimum, is an intermediate, while this and this are two transition states. Okay. Now, seeing this profile as it looks now, and we'll reproduce it on the next page, let's see how does this influence the reaction rate. So to just repeat what we already said, we have this profile which has the first hill which is a little higher and the second hill which is lower, so we finally get the product. Now, in this case, this first hill is the hardest one to get over, and this is the so-called rate limiting step. In other words, since the system needs most energy to get over this hill, it will obviously have enough energy to get over all other lower hills, and thus the rate at which the system gets over the highest hill will limit the rate of the overall reaction. What I find a good analogy of this is a production line, and I'll draw a couple of the caricatures. So if we have a production line where this person A feeds unfinished product to person B, then takes the unfinished product to person C, who then finalizes the product. And if we imagine that this person is slow, it will really what will really control the rate of the production of the final product is the rate at which the person B works. Because since person B is slow, person C will not have anything to do until person B is done. Okay, and so as soon as person B is done with its part of the work, person C will quickly finish it and finalize the product. By the same token, person A will not start accumulating product. It will also finish something, give it to person B, and then wait for a long time until person B is done, and in that time it will not do it. In other words, the overall rate of production here is equal to the rate of production of the slowest worker, right? And that is a surprisingly accurate analogy when it comes to chemical kinetics. And so in our reaction, the first step is the rate limiting one. And that is the subtraction of hydrogen from an alkane by a halogen radical. So this is our rate limiting step. And the rate of this step actually changes quite a bit depending on what X is, which halogen are you using. So I'm going to draw a little table here which depicts the energy of activation as well as the corresponding relative rates depending on the halogen. So this is in kilocalories per mole, 1.2, 4.0, 18.0, and 34.0. And now the rate for fluorine is very high, and it gets even higher as we go higher in temperature, but not by much. Rate for chlorine is relatively high at room temperature, and it gets significantly higher as we increase it. Rate for bromine is very low at room temperature, but it gets into a measurable range as we increase the temperature. Then the rate for iodine is low at room temperature, minus 19, and then it's still low at this temperature. And from these numbers, we can see how well these reactions work. And this one with iodine does not work. Does not work at all. With bromine, it works well at high temperature, but not so well at room temperature, so this needs heating. With chlorine, it already works at room temperature, and this is probably why we chose this reaction as the first one to study. And with fluorine, it works, but it works too well. What does this mean? The reaction is too fast, and so oftentimes this leads to explosions. It's overly violent. So now, in the next stage of this lecture, we will see how does the structure of an alkane influence the reaction rate and how we can achieve selectivity in these reactions.